Hello viewers, welcome to Algebra math class. Today we shall continue with our series on statistics for beginners. So today we are going to be working on the mean and the median of grouped data. In our last video we've been able to talk about mean and median of ungrouped data. So today we are moving straight to the group data. Now looking at the question given to us here, we have these observations being grouped as shown here, and we have the frequency for each of it. Now what we are expected to do is to calculate the mean, and don't forget from the definition of the mean that calculating the mean, we have that the mean is the formula for calculating the mean. We have it to be summation of x over summation f. This means that the summation of, that is the plural of the frequency and the midpoint x, so which is what, fx. So we are going to get the summation and divided by the summation of this frequency. Now the first thing we are going to do is to calculate the summation of our frequency, and from here we know that our summation of our frequency is addition of everything. We have 3 plus 5 plus 6 plus 7 plus 9 plus 8 and 7. This is going to give us 38. That is the summation of our frequency. Now calculating our midpoint, because the midpoint is going to stand for our score. So calculating the midpoint between 40 and 49, just on a rough sketch, if you have 40 plus 49 over 2, and that's going to give us what? 89 over 2, and that's going to give us 44.5. So the midpoint of this is going to be 44.5. Calculating the midpoint for 50 to 59 is going to give us what? 54.5. This is easy to know, just add 10 to it since it is at equal interval, and this is going to give us 74.5. this is going to give us 84.5, and this is going to give us 94.5. So that is our midpoint. Now the next thing for us to do is to calculate our fx. That is the product of our frequency and the midpoint x. So 3 times 44.5 is going to give us, you can use your calculator for confirmation of this. This is going to give us 133.5. And 5 times 54.5 is going to give us 272.5. 6 times 64.5 is going to give us 387. 9 times 74.5 is going to give us 670.5. And 8 times 84.5 is going to give us 676. And lastly, 7 times 94.5 is going to give us 665. Okay? So adding this together, the summation of our fx, this plus this plus this plus this, in total is going to give us 2,804.5. So this is our fx. So this is going to stand for our what? Summation fx. So calculating the mean here, we have that our summation fx, which is 2,804.5, divided by our summation f, which is 38. So this is going to give us 73.8. This is our mean. So this is the average for these data sets. So you can see that the method of group data is quite different from the method of ungrouped data, being that here we need to calculate our midpoint because we need to know the average observation for this range of values. So this is mean. Now we are going to move straight to median of group data. And for calculating the median of group data, it has a formula, and the formula is easy to know. Yes, it is very easy to know. And for that, let me change my pen here. Yeah, let me change to red. So, for our median, we are going to make use of this formula. Let me make it thick. Yeah. So we are using this LB subscript B plus n over 2 minus cumulative frequency before the median class times the class width all over the frequency of the median class. Now, I'm going to say the meaning of all this. Here, we have that our LB okay. So here we have that our LB, L subscript B, is the lower limit of the median class. Is the lower limit of the median class. And our n is the number of observation. Okay, we have that as our number of observation. We have our CFB to be the cumulative frequency before our median class. Okay, so this is the cumulative frequency before the median class. Sorry for using abbreviation. And we have our F subscript M, which is the frequency of the median class. So it's the frequency of our median class. And lastly, we have C, which is the class width, or let me say class size. Yeah, let's call this class size. Yeah, looking at this, from here we know that our lower limit, the first thing for us to determine is to determine our median class. And for you to determine your median class, in our last video you can check, we talked about how to determine median, okay, of ungroup data. Now, the summation F we have here is 38. So when you divide 38 over 2, it's going to give us 19, right? So let's calculate our cumulative frequency, and let's see first. So our cumulative frequency means addition of the subsequent frequencies. And here we have 3, starting with 3. Sorry. And next we have 3 plus 5, right? We have 3 plus the next value, which is 5. So that's going to give us what? Let me put it this way, that we have 3 plus 5, which is going to give us 8. And next one, we have the previous value, which is 8 plus 6, right? Sorry. And which is going to give us 14. So subsequently, like that, 14 plus 9 is going to give us 23. 23 plus the next value, which is 8. Okay? Next frequency value, which is going to give us 31. And to the last value, which is 7, is going to give us 38. So this is going to give us 38. Now let's check. Since our summation F our summation F is 38. Okay, so our median class is going to be over 2, which is 19th value. So where does our 19th value fall? So we can see that it falls on this region. Yes, it falls on this region. So this is going to be our what? Our median class. Let me change the pen so we can see what we mean by the median class. So our median class is going to be this. So which is this? Straight down like this. So it's 70 to 79. So looking at this now, what is going to be our lower limit? So our lower limit is 70, while upper limit is 79. So our lower limit is 70, right? And our number of observation from 40 to 49. Students often make mistake here whereby saying that 40 to 49 is 9. No. So 40 to 49 is 10. We have 10 digits. Okay, when you count from 40 to 49. So here we can say that our n is 10. And the cumulative frequency before the median class. Since this is our median class, so the cumulative frequency before it is what? 14. Okay, that is our cumulative frequency before it. We have it to be what? 14. And lastly, we have our frequency. Our frequency of the median class. So the frequency, since this is the median class, the frequency of the median class is 9. Okay, so the frequency of the median class is 9, while our class size is 10. Oh, sorry, our number of observation can be 10. That is a mistake from my part. It's 38. Okay, our number of observation is the same thing as summation F. Okay, now doing this, we are going to make use of these values in computing our median. So coming down here, we have that our median will now be equal our lower limit, which is 70. We can decide to use boundary if you like instead of using limit. Okay, in bracket n over 2, our n, which is the number of observation, which is 38 over 2, minus the cumulative frequency before the median class, which is 14, all over, okay, we have this closed, times our class limit, which is 10. Everything over frequency of the median class, which is found to be 9. So going forward, we have 70 plus 38 divided by 2 is going to give us 19 minus 14, everything over 9 multiplied by 10. So here we have 70 plus 19 minus 14 is going to give us 5 over 9 multiplied by 10. So we have 70. You have 70 plus 5 over 9, or 5, let's multiply 5 by 10, and here we are going to have 50 over 9. Okay, so going forward, we have 50 over 9. You can solve that using your calculator. So we are going to have 70 plus 50 over 9, because I am doing this without using calculator. We know that 50 over 10 is 5, right? So let's do that somewhere here. We have 50 over 9. 9 in 50, 9 times 5 is 45, right? So you have that as 5. So you can have that as 5.5. Okay? So because 9 in 50 is 45, remainder 5, add 0 to it, 50, so you can have 5.5. So here you have 5.5. And finally, our answer is going to be 75.5. So this is our final answer. One thing you will observe with the median is that the value you are going to get here as the median value must fall within this range from 70 to 75. If it falls outside this range, it shows that what? It shows that your answer is wrong. So you can see that the median class is somehow greater than the midpoint, which is 74.5. So kindly subscribe to our YouTube channel so that you can be notified of our subsequent videos on this series, and we hope to upload more videos. In our next video, we'll be uploading videos on how to do mode of group data and also of ungrouped data, and also try to help us share and like this video, comment. Thank you very much. See you next week. Hello viewers, welcome to Algebra class. Today we shall continue with our statistics for beginners. This is our 4th episode on this series. Today we are going to start with the mode of group data. And in our previous videos, we've been able to look at the mode for the mean. We are able to look at the mean and the median of group data. So today we shall move straight to the mode of group data. And the formula for our mode of group data, we have that mode equals to the lower boundary, okay, LB plus F1 over F1 plus F2 multiplied by C. So we can possibly easily put this in a bracket for easy computation. So where our F1 is the same thing as the frequency of the median modal class minus the frequency before it. So looking at this now, this is our frequency of the modal minus the frequency before, and also our F2 is the same thing as the frequency of the modal class minus the frequency after it. And here our C is the class width. That is, you can call it the class interval also. That means the difference between the lower and the upper. And LB is the lower boundary. So these are the parameters that we have. Now we are going to use this to compute the information given to us there. Now for us to do this, now we are making use of the same formula here. We have that our mode equals LB subscript B plus F1 over F1 plus F2 multiplied by C. So with this, our lower boundary, the first thing we are going to look at is to determine our modal class. And our modal class is where you see the highest frequency, and this is our highest frequency. So this is where our modal class is, which is 25. The highest frequency is 25. So this is our modal class, that is 6 to 10 and 25. So this is what we are going to put into consideration. And for us to determine our lower boundary, we know that our lower limit here is 6. Okay, so you are going to subtract 0.5 from this lower limit 6. So our lower boundary is going to give us 5.5. In my previous video for the median, I decided to use the lower limit directly because you can also do that. But in this case, I'm going to use the lower boundary by subtracting 0.5 from the lower limit plus F1. Our F1, don't forget, is the frequency of the modal class minus the frequency before it. And the frequency of our modal class here is 25. So let me put that in bracket for easy computation. Minus the frequency before it, which is what? 20. That is my F1. Everything over F2, which is the frequency of the modal minus the frequency after it. And the frequency of the modal class is 25. The frequency after it is 23. That is my F2. My F1, I'm going to repeat this, which is 25 minus 20. multiply by my class width, which is 5, from 1 to 5, so which is 5. Now simplifying this further, I'm going to have 5.5 plus 25 minus 20 is going to give me 5 over 25 minus 23 is going to give me 2 plus 5 multiplied by 5. And with this, I'm going to have, and my mode is going to be 5.5 plus 5 over 7 multiplied by 5. So with this, I'm going to have 5.5 plus, 5 times 5 is going to be 25. 25 over 7 is going to give me 3.57. We can add that together. So the mode is going to be 9.07, and approximately my mode is going to be 9. So that will be the height of the student. If the height of the student is in meter or any unit the height of the student is, so we're going to have the same thing here. So this is what I just have. Okay. Now looking at this now, you are going to see that this value 9 must fall within this range of 6 to 10, just like the same thing we did in the median. If it falls outside it, then there's a mistake somewhere. So this is our frequency, the frequency for the modal class. And our final answer here is 9. Thank you very much, and please don't forget to subscribe to my channel. In our next video, we are going to move straight, because we are done with the measure of central tendency. We are moving straight to measure of dispersion. So when Hello viewers, welcome to our math class. Today we shall continue with our episode on statistics for beginners. Before we proceed, kindly subscribe to my YouTube channel. So in our previous videos, we've been able to look at measure of central tendency, and today we shall proceed with measure of dispersion. And the first thing we are going to define here is the range. From the definition of range is the difference between the highest and the smallest numbers in a given set of numbers. Now, looking at the first example we have here, we have the find the range of this set of numbers. So from the definition of range, we know that range is the same thing as the highest number minus the smallest number. And from this observation, we can see that our highest is 20, while our smallest is what? 3. So this is going to be 20 minus 3, which is 17. So you can see that calculating range is very easy, even for group data. Just look at the observation given to you, the highest value minus the lowest value. That is the value of range. And secondly, we are going to look at the mean deviation. The mean deviation. So we are going to consider two cases for this mean deviation. And the first case is when you don't have a frequency. So here we are going to have summation x minus x bar over n. Take note, this is an absolute value. When you say an absolute value of x, it can assume two values, either the positive, that means the value of x can be positive or negative. So the absolute value only take into consideration the positive value. So that is the purpose of the x, absolute value for the x. Now let's consider a situation whereby we have a new data set. We are going to consider the mean deviation for this same data set, 3, 4, 8, 9, 16, and 20. So our observation is 3, 4, as we have up there, 8, 9, 16, and 20. So we are to consider calculate the mean deviation. The first thing for us to do is to calculate the mean. And in our previous video, we've been able to talk about that. Don't forget that the formula for calculating mean, which is x bar, is the same thing as the summation of x over n. That means all this observation must be added together. So we are going to have 3 plus 4 plus 8 plus 9 plus 16 plus 20. everything over how many observations? 1, 2, 3, 4, 5, 6. We have 6 altogether. So calculating the mean of this, so we have our mean, which is the same thing as x bar to be equals to 3 plus 4, 7 plus this, we have 15, plus 25, which is 40, plus this, which is 60 over 6. So our x bar is 10 in that regard. So using this same definition formula to be summation x minus x bar over n, so my mean deviation, I can represent that with MD, is going to be summation of my x minus x bar. That is the positive value, okay, of my x minus x bar. So my x now is 3 minus 10, okay, the positive value of it. The next observation, which is 4 minus 10, plus the next observation, which is 8 minus 10, plus the next observation, which is 9 minus 10, plus the next observation, 16 minus 10, and the last one, which is 20 minus 10. So we are taking the absolute value of the observation. This is going to be over n. How many observations do we have in total? Which is 6. So calculating this now, using the value given to us there, 3 minus 10 is going to be negative 7. Taking the absolute value of that is going to be positive 7. 4 minus 10, you are going to have 6 plus 2. Don't forget, you are taking only the positive value because of the presence of the absolute value. Plus 1 plus 6 plus 10. All over 6. And this is going to give us 7 plus this is 13, 15, 16, 22, 32. So here we are going to have 32 over 6. And that should give us 5.3 something. So that should be our what? The mean deviation. And what's the purpose of mean deviation? This is to see how our observation is far from the average. That is the purpose of mean deviation. Hello viewers, welcome to Algebra Math class. Today we shall continue with our series on statistics for beginners. So today we are going to work on the variance and standard deviation for the ungrouped data. So in our previous video, we've been able to work on the mean deviation for the ungrouped data. So today we shall continue with the variance and the standard deviation. Like I told you, if we're talking about the variance and the standard deviation, this is just looking at the square difference of members from the mean of the data, the deviation from the mean of the data. So today, I'm going to give you the formula for the variance. So the first formula, if it is the population variance, we can use sigma square. Okay, we use this to represent what a variance is. So it's going to be summation x minus x bar, almost the same thing with the mean deviation we did in the last class, squared over n. So the n is the number of what? Observation. Okay, and in this case, alternatively, you can use another method for this, but for the sample variance in which we are going to work on today, we can have x squared to be equals to summation x minus x bar all squared all over n minus 1. So the only difference between these two is that here our n decreases by 1. So that's what we are going to work on today. So for this, we can have this in this form, or alternatively, it can be written as summation x squared over n minus x bar all square. Don't forget our x bar is the mean. So we are going to use these two formulas to solve our example given here. So here we are told that given the following data set 3, 5, 7, 8, 7, find the variance and also the standard deviation. Yeah, before I proceed, don't forget also that when we talk about the word standard deviation our standard deviation, I'm going to use STD to represent that, is the same thing as the square root of variance. So whatsoever you get for your variance, just find the square root. So that is equivalent to our standard deviation. Now for us to do this now, the first thing we are going to do, since we are calculating the variance, so our variance is going to be, let me use S squared, it's going to be, let's use the first formula, x minus x bar all squared over n minus 1. So we need to calculate our s bar first. So calculating our s bar, which is the mean. In our previous video, we've shown how to calculate our mean. So that means addition of everything over the number of observation. And that's going to be 3 plus 5 plus 7 plus 8 plus 7. So we're dividing everything by number of observation, which is 5. So this is going to give us 30 over 5. And our mean is going to be 6. So now making use of the formula here, which is summation of x minus s bar. So our variance will now be equals to our x, that means each of the observation minus the mean. So here we are going to have the first observation, which is 3 minus 6 all squared, plus the next observation, which is 5 minus 6 all squared, plus the third observation, 7 minus 6 all squared, plus the fourth one, 8 minus 6 all squared, plus the last one, which is 7 minus 6 all squared. Okay, we are dividing everything by our n, which is what? Which is 5. So let's use of the population variance. So I'm going back to this. So that means instead of using n minus 1, I'm going to use this in this case, because here we assume that we are working with population, not the sample in this case, because the question does not indicate whether it is sample. So we regard our information given as the population, So solving this now, here we are going to have 3 minus 6 all squared is going to give me 9 plus 1 plus 1 plus 4 plus 1 all over 5. And this is going to give me 16 over 5, which is equivalent to 3.2. Mind you, don't forget that from here, our standard deviation, that's for our variance, right? So here, calculating our standard deviation is the same thing as saying the square root of our variance. And don't forget our variance here is 3.2. So this is the same thing as saying square root of 3.2. So our standard deviation in this case is going to be 1.79. So this is for the first method. This is for the first method. Using the second method, which has been given to us here to calculate. So we are going to make use of this second formula to calculate our variance. So here we have our variance to be equals to summation x squared over n minus x bar squared. So we want to check if we are going to get the same answer for this. So here we need to know our summation x squared first. And since the summation x squared equals, that means each of the observation square, each of the observation, that is 3, 5, 7, 8, 7, we are squaring each of it, is going to be 3 squared plus 5 squared plus 7 squared plus 8 squared plus 7 squared. So this is summation of our x squared, and that is going to give me 196. Okay, and don't forget our s bar square. So in this case now, our variance, my variance here is going to be summation x squared, which is 196 over 5, which is the number of observation, minus x bar all squared, and my x bar in this case from here, my x bar is 6, so minus 6 squared. So this is going to be 196 over 5 minus 36. So solving this further, I'm going to get 3.2. So calculating the standard deviation also is still going to be square root of 3.2, which is going to be what? 1.79. So this is for the standard deviation and also for the variance of what? Of ungroup data. Before I leave, I have to tell you this. This can be extended to when you have frequency of number. So that is, our variance, when frequency is involved, can be equals to summation f, okay, into bracket x minus x bar all squared all over summation f. So that's the only difference. Instead of using n here, we are going to use f and f here too. So those are the two formula that we have in this case. Okay, so you can use this to solve this as a classwork and put the answer in the comment section, such that when you have x and we have f, we have 0, 1, 2, 3, 4, and we have the frequency to be 3, 2, 4, 1, 2. So I want you to use this to calculate the variance and also the standard deviation. Don't forget that the standard deviation is just going to be the square root of our variance, which is summation f into bracket x minus s bar all squared over summation. In my class, today we shall be working on episode 7 of our statistics for beginners. So today we're asked to calculate the mean, the variance, and the standard deviation for the grouped data. So the first thing we need to do is to get the middle value. And for us to get the middle value, since our class interval is 50 to 59, then we can say that our mid value will be equals to the average of the two. That is, we are going to say we are 50 plus 59 over 2. And 50 plus 59 is going to give us 109 over 2, which is the same thing as saying 54.5. So our mid value here is going to be 54.5. If the same thing is done to 60 to 69, so here we are going to have 64.5. And here we are going to have 74.5. Here the middle value is going to be 84.5. And lastly, don't forget, here the interval is from 90 to 100. So our mid value is not going to be 94.5, but instead the average is going to be 95. So that is our mid value. Okay? And looking at our frequency, don't forget that for us to calculate the mean for the group data, we have that our formula for calculating the mean is summation fx over summation f. So we need to know the summation of our frequency, that is 3 plus 5 plus 9 plus 12 plus 8, and that is going to give us 37. Okay, so now we need our fx, that means frequency multiplied by x. So using your calculator, 3 times 54.5 is going to give us 163.5. And 5 multiplied by 64.5, here we're going to have 322.5. Here I'm going to have 670.5. Here I'm going to have 1014. And here lastly I'm going to have 760. So calculating the sum of everything, that is adding everything together, the sum is going to be 2930.5. So with this, my mean is going to be 2930, which is the summation of fx over summation f, which is 37. And from this, my mean is going to be 79.2. So looking at my formula here, there's a need for me to put S bar. So don't forget that the mean is the same thing as saying X bar. That is from our previous video. I've explained the notation used for mean, so we can use S bar. So what we just need to do here is to get x minus x bar and square it. What do I mean in getting this? For the first value, it means x. My x is 54.5. That is, I have 54.5 minus x bar, which is 79.2. So I'm going to subtract this and square. You understand? So the same thing will be done for the second one, that is 64.5 minus 79.2, then squared it. So using your calculator, 54.5 minus 79.5 squared is going to give me 610.09. And for the second one, I'm going to have 216.09. I'm going to have 22.09. Here, I'm going to have 28.09. Here, I'm going to have 249.64. Okay, so lastly, we are going to do F. And the reason why I'm doing this, from the formula of calculating my variance, from our previous video, I gave you the formula for variance, which is summation F into bracket x minus s bar all squared over n minus 1, or you can say summation f minus 1, either way, or you can use n minus 1. So here there's a need for me to get f multiplied by x minus s bar all squared. So here the first value here, using my frequency multiplying it with this, so I'm going to have 1830.27. Here I'm going to have 1080.45. I'm going to have 198.81. Here 337.08. 1997.12, and the summation of everything is going to give me 5,443.73. You can use your calculator for that. So calculating my variance in this sense, it shows that the summation of f into bracket x minus s bar all squared gives me 5,443.73 all over summation f, which is the same thing as 37 minus 1. Okay, and with this shows I'm going to have over 36, right? So dividing this gives me 151.2. And lastly, we are to get variance and the standard deviation. So our standard deviation, from the last video, we know that our standard deviation, SD, is the same thing as square root of our variance, which is the same thing as square root of 151.2, and my standard deviation is going to be 12.3. So that is it for the grouped data. So kindly subscribe to my YouTube channel. In our next video, we are moving to more important topic in statistics. Until then. Hello viewers, welcome to another class. Today, we want to estimate regression parameters. So, we have this general regression form. Don't forget that this is a multivariate form. And here we have that our y equals to xb plus what? Plus epsilon plus e, which stands for the error term. And this is the parameter we want to estimate. So before we proceed, don't forget that our e is normally distributed with mean 0 and variance sigma square. So we can also estimate that. But this is our area of concentration. So we have this. Rewriting this given equation, we can rewrite our E to be equals to y minus xb. That is, we're looking at the deviation of the observation, okay, from the mean. So that is the, what's it called, the error. So with this, our epsilon prime epsilon is the same thing as having y minus x beta prime, which stands for the epsilon prime of transpose. Either way, let me call it the transpose. Y minus this. Okay? So let this be what? Be Q. So by so doing, we want to distribute. So we can have the Q to be y prime multiplied by y. Don't forget, this is a matrix multiplication. So we need to be very cautious. We're going to have y prime y multiplied by xb. We're going to have negative y prime xb. X beta multiplied by y, we're going to have beta prime x prime y. Now, I need to explain something here. Looking at this is a transpose value. So I'm using prime in case of transpose. So I didn't say s prime b prime. No, it's going to be what? In reverse order. So that is when you have a, b, c transpose. So if you want to bring this out, it's going to be c prime, b prime, a prime. That's the rule. Okay, so the same thing is being used there. So the last one is to multiply this by this. So here we're going to have plus b prime x prime xb. So there's another thing we need to take note of, and that is the issue of transpose. Looking at these two, we're going to see that y prime x beta, if this is being transposed, it's going to be the same thing as beta prime x prime y. That shows that the transpose of this is the same thing as this. So we're going to be the same, they're going to be the same. So here we have q to be equals to y prime y minus 2 beta prime x prime y plus beta prime x prime x beta. The multiplication is possible because we take cognizance of the order, the dimension of this. So if the dimension contradicts, then the multiplication cannot be done. From this equation, we're going to differentiate with respect to the parameter we want to estimate, which is the beta. So here, I'm having my dq, the beta. I'm going to differentiate this q with respect to beta and equate the answer to 0. So with this, I'm going to have differentiating this with respect to beta. No, there's no beta, no parameter here. It's going to be 0. Differentiating this with respect to beta. So here I'm going to have negative 2x prime y. Differentiating this with respect to beta, this is like having beta squared. So differentiating, so it's like you having beta prime x prime y. It's like this is being squared. So this is going to come to the back. So we have 2x prime x beta equals to 0. This has been estimated. So with this, we can have 2x prime x beta equals to 2x prime y. Dividing both sides by 2. Okay? So don't forget, this is a matrix multiplication. So we want to get rid of the coefficient of the beta, which is s prime x. So this is going to be beta cap equal x prime x inverse is a matrix x prime y. So this is the general form of our parameter beta. Now we want to estimate. And part of what we're going to do here is that we've known the value of beta to be this. So how do we get our expectation of beta and also the variance of beta? We have beta cap to be equals to x prime x inverse x prime y. So here we want to find the expectation of our beta cap. And our objective is that to show that it is an unbiased estimate. And don't forget that we have y equals to x beta plus e. And expectation of y is going to be x beta plus the expectation of epsilon. And recall that our epsilon follows a normal distribution with mean 0 and variance sigma squared. That shows that expectation of epsilon is going to be 0. So our expectation of y is going to be x beta. So here I'm having the expectation of x beta cap. So which is the same thing as saying x prime x inverse x prime, the expectation of y. Now, because these are predictors variables, right? The x are the predictor variables. Okay. So here we have x prime x inverse x prime. Expectation of y is the same thing as x beta, which is the same thing as x beta. Now, looking at these two matrices, s prime x inverse multiplied by x prime x. So this shows that this is just going to be what? It's going to be 1. So here we can have our beta. So it shows that it's an unbiased estimate. Secondly, we need to estimate the variance of beta also. We have the variance of beta cap to be the variance of the beta cap, which is the same thing as this. We're going to plug in the value of this x prime x inverse s prime y. Here, I'm going to take you through a quick review of something. Don't forget that if you have variance of ax, whereby a is a constant, the rule is that we're going to have what? A squared variance of x. The constant is going to be squared. And if it is in matrix form, if you want to leave it in matrix form, it's the same thing as a variance of x a prime. So I'm going to use this second approach. Okay, so this is going to be my constant. This is going to be my a. X prime x inverse x prime is going to be my a in this regard. So using the same approach, I'm going to have my a coming out, which is s prime x inverse x prime. So the variance of my y, variable y, and then the transpose of this, a transpose. So I'm going to take the transpose of this, and taking the transpose from the previous explanation I did is going to be in reverse order. So this is going to be x prime x inverse in reverse order. So it's going to come like this. And the transpose of s prime is going to be x. So we have x prime x inverse. Don't forget that the variance of y is the same thing as sigma squared. So I can have this as sigma squared. That is the variance of y is the same thing as sigma squared. So here I have my x prime x inverse x prime. Then I'm having my x here. And here I'm having my x prime x inverse. So this goes. So therefore I can say that the variance of my beta cap is going to be sigma squared x prime x inverse. So that's the second thing I'm going to do. And lastly is looking at the point estimate of our parameter beta. I'm going to clean this. So doing that, I'm going to have, for the point estimate, the rule is that you have the parameter you want to take. For instance, we have b naught plus b1 x1. This is the general form of a linear regression. Okay, so for instance, you are interested in estimating b1. The general form is very easy, which is your b1 minus the expectation of your b1 over what? The standard error of your what? Of your b1. That's just the general form. The parameter itself minus what? Minus the mean of the parameter over the what? The standard deviation, standard error of the parameter. Standard error of the parameter. So that is just the general form for what? Your point estimate. So here I'm going to stop. In my next video, I'm going to proceed by looking at some other factors and properties of what? Of regression. Thank you very much for watching my videos. Please kindly subscribe to my YouTube channel. See you next time. Thank you. Hello viewers, welcome to the class. Today we are going to work on the analysis of variance known as the ANOVA. So I'm going to put you through the basic model of the analysis of variance and also on the decomposition of the sum of squares. So generally we should know that the model for the analysis of variance is Yij equals mu I plus Eij. And one of the basic reason for studying this analysis of variance is for us to look, the application of ANOVA is majorly used in any design of experiment, be it in the agriculture or in any other field. So we are going to look at the treatment effects. How does the treatment perform? Is there any difference in the treatment, or there's no difference? So these are the things in which we are going to look at. But there's a need for us to know the statistical background regarding this. So here we have our Yij. This talks about what? The observation, okay? And we have our mu I. So the mu I is the same thing as the what? As the treatment mean. So this is the mean of the treatment being assigned. And we have our Eij, which is also known as what? The random error. So mu I, this model can also be written as our Yij equals mu plus tau I plus EIJ, where our mean height, which is the treatment mean, can be split as the what? The overall mean, and also what? As the treatment effects. So our mean is known as the what? Overall mean, and our tau high is known as the what? The treatment effect, where our EIJ is still the same thing as our what? Random error. Because statistically speaking, for every experiment, we should give room for what? Error, because no experiment is perfectly carried out. So there is possibility of you having an error. So we need to estimate the error also. So now with this is going to give us a guide on how to decompose our sum of squares, in which all these general formula we know about ANOVA. How do we get this formula? This is what we want to work on. So this is going to take, looking at this, if you estimate this population mean, which is known as the overall mean, okay, which is also known as what? Our y dot bar, okay, the estimate of it. So don't forget that we have our observation equals this. So this is what I'm going to use to estimate my what? My sum of squares. So now, under the decomposition of the sum of squares, I have that my SS total. When I use the word SS, this means what? Sum of squares. So that's the meaning of SS. So for the total, that means for the general treatment, so we have our SS total to be double summation, where my I sum from what? 1 to what? A, and my J sum from 1 to N, Yij, okay, which is the individual observation, minus the what? Minus the overall mean square. And if you look at this, don't forget that our I sum from 1 to what? A, and J sum from 1 to N. So when we get to the two-way ANOVA, which is known as the RCBD, which is the randomized, completely block design, then we can talk about the blocking effect and also about the treatment effect. But in this case, we are not considering the blocking. Okay, we are only limiting it to the what? To the treatment effect. Now, we want to decompose this. Okay, so what we want to work on is the decomposition of our what? Of our SS total. So how do we decompose our SS total? So that's what we want to work on. So we have our SS total to be double summation. In this work, I'm going to omit the use of the notation that is I to A, J to N. Okay? But when I need it, I'm going to make use of it. So I have Yij minus y bar dot squared. So decomposing this is the same thing as saying my double summation Yij introducing minus yi dot bar plus yi dot bar minus y dot bar all squared. Don't forget, this is what we have initially. So my yi dot bar, this is known as what? Treatment mean. This is the same thing as the treatment mean. Okay? So minus yi dot bar plus yi dot bar can cancel out, which shows that this is still the same thing as this. Just that for me to get my decomposition well, I need to introduce the treatment mean. Okay? So using this, if you want to distribute this, that means factorizing this, or let me say expanding this. Okay? This is the same thing as saying yij minus, just take these two, okay, call these two A, this B. It's like you having A plus B. And don't forget, if you want to factorize A plus B to the power of 2, you are going to have what? A squared plus B squared plus 2AB. Right? So the same thing is what I'm going to use there. So you are going to have A squared plus B squared plus 2AB. So that's what I'm going to use here. So my A, which is yij minus yi dot bar squared plus double sum yi dot minus y dot bar squared plus 2 double sum, which is AB. Now we have yij minus yi dot bar minus y dot bar. This is the same thing as the cross product, right? Okay. A squared plus B squared plus 2AB. This is just what I did. Now, leaving these two, let's just talk about these cross products. Okay? Now, we have two double sums yij minus yi dot bar minus y dot bar. So, this is the same thing as you having 2. Let this be intact, then let's distribute this. So let me just go down a little bit. So here I have 2 double sum yij minus yi dot multiplied by yi dot minus 2 double sum yij minus yi dot multiplied by what? Y dot bar. So with this, solving this is the same thing as you having 2, and don't forget, I ranges from 1 to A, my j from 1 to what? N. So my I sum from 1 to A, my j from 1 to N. So I have 2 y bar I dot summation, okay? I from 1 to N. Since this sum from 1 to N, so my I sum from 1 to A. So since my j sum from 1 to N, then I can say this is the same thing as what? We adding NYI dot bar minus NYI dot for this. Okay? When you take this sum to go in here, you have the same thing as this. Don't forget that mathematically that y bar is the same thing as summation x over n. Right? That is summation x equals n y bar. We have this mathematically. So this is what I'm making use of here. So minus this denominator, I have 2 y dot bar. Okay. So here I have the same thing will be used. Sum from 1 to A, NYI dot minus NI dot bar. So looking at this minus this gives 0, this minus this gives 0. So this shows that we have what? 2 into bracket 0 minus 2 into bracket 0 equals to 0. So coming up to this, we can see that the cross product is the same thing as what? 0. So we can see that the cross product is the same thing as what? 0. So we can say from here, I think I will have to clean this. So this is what I've been able to prove, that this cross product is the same thing as 0. So cleaning this for me to be able to show what I want. Okay, let me just clean this. So that means the cross product does not exist again. So double sum yij minus y dot bar squared. This is the same thing as our what? SS total, which is the same thing as what? SS error. This is my SS error plus, sorry, S dot SS treatment. So for the decomposition of the sum of squares, your SS total is the same thing as SS error plus what? SS treatments. So this is what you have here. And what we get here will be used. Okay, let's talk about the mean square error, mean square total, and mean square treatment also. So with that, we can draw our ANOVA table. So I can do. So I'm going to do this. So we have our mean square total. So there's nothing like mean square total, mean square error, which is also known as what? SS error, over the degree of freedom. How do we determine the degree of freedom? Yeah, before I can proceed with this, I have to give a little analysis regarding degree of freedom. Take for instance, we have an experiment before even moving straight to the mean square error. Take for instance, just take note of this. So we are coming back there. I'm a farmer. Okay, I have a plot of land. So in my plot of land, I intend to plant a maize. Okay, so this is my first treatment. I have my Y1. This is the first plant. I have my what? The second observation. In the first row, second column, first row, third column, and I also have what? First row, fourth column. Okay? So I have the same thing here: 2, 1, 2, 2, 2, 3, 2, 4. Okay? 3, 1, 3, 2, 3, 3, 3, 4. So here I'm having plant A, B, and also C. So these are the plots. Okay? Now, with this is the sum. I have my yi dots. This is the sum for the first row, for the second row, and also for the third row. Here, I can have the mean, which is the same thing as yi dot bar. That is this divided by what? 1, 2, 3, 4. Here, you can have your y2 dot bar, and here, y3 dot bar. And overall here, this is the same as y dot dot, which is known as what? We call this the grand mean, or the overall mean, right? You can call this the grand mean or the overall, no, sorry, the grand total, or the overall total. So y dot dot bar is called the grand mean, or the overall mean. So this is what we have. So for you to get your mean square, don't forget the A stands for what? For the row. I stand my high start from what? 1 to A. My J, which represents the column, 1 to what? N. So my A is for the row, my N is for the what? The column. So if you want to know the total units in this case, total units, let me call that capital N, is the same thing as what? Number of rows times number of columns. So we have how many rows? 3 rows multiplied by what? 4 columns. In this experiment, here I can say my A, in this experiment, A is 3, N, which is column, is what? 4 columns. So my N is the same thing as A multiplied by small n. So in this experiment, it's going to be what? 3 times 4, which is 12 units. So for our mean square error, or mean square error, yeah, is the same thing as SSE over n minus a, while my mean square treatment is the same thing as what? SS treatment over what? Over a minus 1. So for your F statistics, for our F statistics, we call it the F observe. You use the same form, you use the formula MS treatment over what? MS error. So you as a statistician or as a consultant statistician, so although we have some softwares to do this, you can use your SPSS, R, SAS, and some other softwares like that to do this. But you as a statistician, we call upon, once you calculate your F naughts or F observe, so the value of your F observe, for you to determine if the experiment can be rejected or you do not reject the hypothesis of the experiment. You know, your hypothesis, under the normal null hypothesis, your normal null hypothesis is that what? The treatments are equal. That is the null. But your alternate hypothesis is that at least one treatment is not equal to 0. That's the alternate hypothesis. So there's a need for us to get our F table value. But nowadays we don't make use of F table. Although you can still make use of F table for examination purpose, but we use P value, because when you run the software, after giving you the value for your F observe, immediately you are going to get a P value. Then you can make your conclusion based on your P value. But if you want to calculate your F table value, then you can make use of what? F, the degree of freedom, depending on your alpha, okay? Level of alpha, I don't know, maybe you are using 0.05, but you make the degree of freedom here is going to be what? The degree of freedom of the treatment, because here you're having MS treatment as the numerator. And what is the degree of freedom of the MS treatment? Which is A minus 1. And the degree of freedom for the MS error, which is what? N minus A. Okay? Then, depending on your level of alpha given to you, okay, you can use 0.05, you can use 0.01, depending on how the experiment, how you want the experiment to be, okay, and the level of alpha you are considering for the experiment. Now, what are the conditions for you rejecting a particular experiment, your hypothesis, or you not rejecting your hypothesis? This is the condition. That is, if your F observed, the value you calculate or F calculated is greater than your F table value, okay? If it is greater, you do what? You reject H naught. So when you reject H naught, then your conclusion is that there's significant difference in the what? In the means or in the treatment means. That means there's significant difference in the treatment means being compared in the experiment. Okay? But if otherwise, if it is not greater, maybe it is less, the value is less, then you do not reject. you do not reject. The same thing with p-value. In p-value, you compare your p-value with 0.05. And if the p-value calculated is less than 0.05, you are going to reject the null hypothesis. But if your p-value is greater than 0.05, you do not reject the hypothesis. So those are the conditions. Now, typically, we have ANOVA table as this. Under your ANOVA table, we have the source of variation. We have the degree of freedom. We have the sum of square. We have the mean square. And we also have what? The F. For the source of variation, we have the treatment. We have the error. And we have the what? The total. So for the treatment, the degree of freedom for the treatment, don't forget, is what? A minus 1. For the total, we have what? N minus 1. So, for you to get your error, the degree of freedom for error, although I said N minus A, but how do we get N minus A? Don't forget that treatment is the number, A is the number of rows, just subtract 1. For the total, which is AN, okay, that means you calculate all the units, subtract 1. But for error, you calculating error is the same thing as saying degree of freedom of total, which is N minus 1. Okay, equals to the degree of freedom of error, let's call that E, plus the degree of freedom of what? Treatment, which is A minus 1. So to get the value of E is like saying N minus 1 minus A plus 1. So minus 1 plus 1 cancelled, you have N minus A. That's the degree of freedom of what? Of error. So this is the same thing as what? N minus A. Also, to get our sum of square, don't forget the sum of square for treatment, the formula has been given to be double summation yi dot bar minus y dot bar all squared. And also, for the SS error, double sum yij minus yi dot bar all squared. And for the total, double sum yij minus y dot bar all squared. And for your mean square, is the same thing as what? SS treatment over A minus 1. For the error, SS error over N minus A. And for your F value, your F is the same thing as MS treatment over MS error. That's all. Then you are done. Although, for calculating the sum of square treatment, we have an alternate formula. Here I'm saying SS treatment is the same thing as what? Double sum yi dot bar minus y dot bar all squared. You can also have it as what? 1 over, okay? 1 over what? You can use 1 over B, which is the number of columns, okay? Summation yi dot squared. Not span this time, we are not taking the mean, just the total. Minus what? Y dot over what? N. So we are going to end the class. Oh, sorry, here I need to put squared. So we are going to end the class now. Don't forget to subscribe. See you next time. So you are the math class. Today we want to solve this question on the analysis of variance. Here, our interest is centered in the effect of tube conductivity. So we have the data set on the TV tube coating data, which is treatment 1, 2, 3, and 4. So the first question here says that suggest the experiments to use. Now looking at this, since our interest is on the TV tube coating data, okay, we just want to see if there's significant difference in the mean of the tube coating data. So for the first question being asked here, so we're going to use what is known as this is a complete randomized design. And if you ask me why, here there's nothing like blocking, so we are not doing any blocking. So other way known as one-way ANOVA. So this is the one-way analysis of variance. So the second question is that write down the mathematical model for this. So writing down the mathematical model, you can check some of my previous videos for the proof of this model, how the model is being gotten, the breakdown, the composition of the one-way ANOVA. I have it. You can, at the end of this video, I'm going to attach it to it. So having this, the model for the CRD will be Yij equals mu plus tau I, which is the treatment, plus the error term, which is the Eij. Don't forget that my I is from 1 to 5 and my J is 1 to 4. So we have J 1 to 4 and I, the rows, is 5. And before I proceed with this, there's a need for me to talk about the constraint. So we'll talk about the constraint. So the constraint we have is that our summation of tau I, where I is from 1 to 5, must be equals to 0. That's the general constraint that we have. And talking about the distribution of our error term is normally distributed with mu and variance sigma square. So the third question is to analyze the experiment and comment on the result. So this is the analysis of the experiment. So doing the analysis of the experiment here, for one-way ANOVA, the general formula for the one-way ANOVA, the first thing you need to calculate is the sum of square total, which is known as SST0, which is double sum your Yij squared minus y dot dot squared over capital N. Here, my y dot dot over capital N is known as the correction factor. If you check my previous video on one-way ANOVA, you're going to see how I got this, the general formula for the SS total. You can check my video. So now, calculating this, there's a need for us to know the grand mean and the grand total, which is y dot dot. So here, I'm going to have yi dot. That is the sum of the rows. The sum of the rows. Okay? So this is the treatment. So here, summing this row-wisely, I'm going to have 207. That is 56 plus 64 plus 45 plus 42 is going to give me 207. And for the second line, I'm going to have, you can use a calculator to confirm these values, 201. And thirdly, I'm going to have 202. Then I'm having 196. And here, I'm going to have 200. So here, yi dot bar. So my yi dot bar can be calculated by making this 207 divided by the total, okay? The total here, which is 4. So 207 divided by 4 is going to give me 51.75. 201 divided by 4 is going to give me 50.25. And 202 divided by 4 is going to give me 50.5. 196 over 4 is going to give me 49.0. And lastly here I'm going to have 50.0. So y dot dot, which is the grand total here, summing these together, this column together, I'm going to have 1006. And for the grand mean, which is y dot dot bar, is going to give me 50.3. That is calculating the average of this column. Now coming back to my sum of square total, my summation yij all squared is just going to be here. What do I mean by summation yij all squared? It means that we are summing each of these observations, that is 56 squared plus 64 squared, up to the last observation, which is 41 squared. So here I'm having 56 squared plus 64 squared up to the last individual observation, which is 41 squared, minus y dot dot, which is 1006 squared, over capital N. Then how do we determine our capital N? Now coming here, we have that our A equals to 5, and my N is 4. So my A is 5, calculating the 1, 2, 3, 4, 5. My N is 1, 2, 3, 4. So with that, my capital N is the same thing as 5 times 4, which is 8 times N, which is 20. So here, using that, I have my capital N to be 20. So summing up the observation, here I'm going to have 51,940 minus the correction factor. 1006 squared over 20 gives 50,601.8. Subsequently, this is what I'm going to use for my correction factor. So my SS total gives 1,338.2. That is my SS total. So after that, there's a need for me to calculate my sum of square error. Don't forget the formula. The formula says that SS total equals to SS error plus SS treatments. So I've calculated my SS total. There's a need for me to calculate my SS treatment. So calculating my SS treatment, which is SS treatment equal, I'm going to use two formulas here, but the first formula is double summation y I dot bar minus the grand mean squared. So using this formula, we're going to have yi dot minus y dot dot. Looking at my yi dot here, the first one is 51.75. Here I'm having 51.75 minus y dot dot bar squared, which is the grand mean, 50.3 all squared, plus up to the last mean. My last mean here is 50.0. So I'm having 50.0 minus 50.3 all squared. So summing this over, here, don't forget that I'm having double sum. So the first one is summing to n. So I'm having n multiplied by all this. And don't forget my n, the value of my n is 4. So multiplying this with the sum in the parentheses, I'm going to have 3.925. That is the sum of the parentheses. And this gives 15.7. So that is my SS treatment. So having gotten my SS treatment, I can easily get my SS total, SS error. My SS error from here will be equals to SS total minus SS treatment. And that's going to be SS total, which is 1338.2 minus 15.7. My SS error is going to be 1322.5. Yeah, before I proceed, like I said earlier on, there's an alternative way of calculating SS treatments. And then the alternative approach for calculating SS treatments is using this formula, which is SS treatment equals to 1 over n summation yi dot squared minus the correction factor. And this is just going to be 1 over n, which is 1 over 4, yi dot squared. Looking up here, my I dot is 207 for the first one, 201 for the second one, up to 200. So this is just like having 207 squared plus 201 squared, and to the last one, which is 200 minus the correction factor. So here I'm going to have 1 over 4 multiplied by 202,470 minus the correction factor, which is 50,601.8. So finally here I'm going to have 15.7, which is the same thing as the previous one we've gotten. So now we've calculated our SSE, SSR. Let me just write it out again. Here, my SSE is 1322.5. SS total is 1338.2. SS treatment 15.7. So with that, we can easily calculate our mean square error. So here, the formula for calculating my MSE, which is the mean square error, is the SSE over the degree of freedom of the SSE, and that is n minus a. Like I said earlier, you can check my previous video to see how I got this. Here I got 1322.5 over capital N is 20 minus our a, which is 5, and this gives 88.17. Secondly, we have the MS treatment, which is SS treatment over the degree of freedom, which is a minus 1. And my SS treatment is 15.7 over 15 minus 1, which is 5 minus 1, which is 4. So this gives 3.925. So to calculate my F, the formula for calculating F is MS treatment, in this regard, we are no longer using our SS total over mean square error. So my mean square treatment, which is 3.925 over mean square error, which is 88.17, gives 0.445. So using your calculator, you can check your F table. If you want to check your F table, you're going to use F. You're at 0.05. You can check that, okay, which is 0.95, comma mean square error for the treatment, which is 4, comma mean square error for the error, and sorry, the degree of freedom of treatment and the degree of freedom of error, which is 15. So what you have, compare it. But here I'm going to use p-value. My p-value, I use my calculator to get my p-value, happens to be 0.774. So lastly, for my comments with this, my comment is just going to be like comparing, using p-value to make conclusion. Since the p-value is greater than 0.05, which is our alpha level, okay, hence we do not reject the null hypothesis. Then you're going to ask, I didn't state any hypothesis. The hypothesis has been explained at the beginning of the class, which is what we are working on, that there's no significant difference in the effects on tube conductivity. So we reject the null hypothesis and conclude that there is no significant difference in the 4 types of coating of TV tubes. Thank you very much for watching. And before I leave, please just know that here you can be asked to calculate the LSD, which is the least square difference, to know which one is significant. Since there's no significant difference, then you can calculate LSD. Thank you very much for watching my video. Please kindly subscribe to my channel. See you next time. Thank you. Hello viewers, welcome to Algebra class. Today we shall be talking about the randomized block design. So when we talk about the word randomized block design, this is just an improvement on the complete randomized design, but in this case we consider what is known as the blocking, okay, and also put into consideration the nuisance factor. So talking about the statistical models, there are two things we need to consider when we talk about the RCBD models, statistical models. So the first is to talk about the mean models, and secondly we talk about the effect model. So when we talk about the mean model, for the mean model we have that to be Yij subscript ij equal mu ij plus Eij. So what does this represent? When we talk about the mu ij, this represents the observation of the height treatment and also what? And also the jet blocking. So we need to take note of this jet block And when we talk about the mu ij, here we talk about the ith treatment and jth blocker. And while our eij is the same thing as the random error. So don't forget that our I tends to from 1 to A, and also J is from 1 to B. So having known this, secondly, we're going to talk about the effect model, which is the second form of the model. And don't forget, this effect model is what we are going to make use of. So when we talk about the effect model, here we have that our Yij equal mu plus tau I plus beta subscript j plus Eij. And in this case, our Eij is normally distributed with mean 0 and variance sigma square. So, highlighting the meaning of this, here our mu here is going to be the grand mean. Our tau I, this is going to be our ith treatment effect, the treatment effect. Y beta j is going to be the what? The block effect. And as usual, our Eij is going to be our random error, and don't forget the distribution of our Eij. So with this, there's a need for me to talk about the parameter constraint. So when we talk about the parameter constraint, this is very important when you state the model. So you need to state the parameter constraint. Here we have that our tau I, where I ranges from 1 to A, the summation of it is going to be 0. Also, the second parameter used here, which is the beta j, where j sum from 1 to B, is also 0. So take into consideration these two parameter constraints. So with this, we can proceed by looking at the sum of squares. So how do we estimate our sum of squares? So by doing that, we know that our sum of square total, which is known as the SS total, is the same thing as here we're going to have the double sum version, where here I have my A from I from 1 to A, and also my J from 1 to B. Okay, summation Yij, that means the observation across I treatment and J block, minus Y bar dot dot, which is the grand mean squared. So decomposing this can be decomposed as double summation. So here we have Yij, which is that of the observation, minus Yi dot, which is the treatment effect, minus Y dot j. This is the mean across the block. So the first one here, this is the mean across the treatment, and this is the mean across the block. So plus Y bar dot 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 dot, which is the grand mean, plus Y bar dot, which is the treatment mean, Y dot dot, which is the grand mean, plus Y dot j bar minus Y bar bar all squared. Then you're going to ask me, why do we have this? Yeah, this is a very good question. Asking, why do you have this to be this? Now, when you look at this, you can see that, okay, let me just give a little illustration here. We want to show that the left hand side is the same thing as the right hand side. So if you take away this minus the treatment mean, which is yi dot, plus this is going to, you are going to have 0, minus this plus this is going to give you 0, right? Plus y bar dot dot minus y bar dot dot, you're going to have 0. So you're going to be left with yij minus y bar dot dot, which is the same thing with the what? With the left hand side, all squared. So this is form of decomposition. We decompose our sum of square total. So by this decomposing the sum of square total, we can have this to be decomposed as double sum yij. Don't forget, doing this, we're going to conclude that, make the assumption that our cross product is 0 in this regard. And if you try to, the same thing, you can watch my video on the CRD, how I show that my sum of square, the cross product is 0. So we have this squared plus y bar I dot minus y bar dot dot squared plus double sum y bar dot j minus y bar dot dot squared. Now looking at this, here we have that this is my sum of square error, this is the sum of square treatment, and this is my sum of square block. And don't forget, this I from 1 to A, j from 1 to B. The same thing with this, I is from 1 to A, j is from 1 to B. So decomposing this further, so here we have that our sum of squared treatment is the same thing as B sum from 1 to A yi dot bar minus y dot dot bar all squared. Don't forget, this is what I brought here. Likewise, my sum of squared block, you're gonna have A sum from j from 1 to B y dot j bar minus y dot dot, which is the grand mean, squared. Now for the first one, this can be written in the form 1 over b summation yi dot squared, okay, that is summation across the row, minus the correction factor. The correction factor can be written as y dot dot squared over n. Don't forget, my n is the product of A and B. So this also can be written in the same form, like we are going to have 1 over A summation y dot j squared minus the correction factor, which is y dot dot squared over n. Either way, you're still on track. And don't forget, my sum of square total, which is double sum yij minus y dot dot bar all squared. Also, this can be written in the form double summation yij squared minus y dot dot squared over n. So this is what we need to focus on and pay attention to. So with this, having done this, then we can move to the mean square error. So for the MS treatment, which is the same thing as the SS treatment, over the degree of freedom, which is going to be what? A minus 1. For the MS block, so we have this to be what? The SS block over B minus degree of freedom. And our MSE, which is the same thing as what? SSE over what? A minus 1, B minus 1. And don't forget, from here, we can get our SSE. And our SSE is just SS total minus, because computing SSE can be cumbersome, so it's better you just use this approach, SS total minus SS treatment minus SS block. So with this, you can get the sum of square error. And developing the test statistics for this, from here we have that our F, observe, is the same thing as the MS treatment over MSE. That is for the first one. Okay, so you can also have it as our F also for the blocking. You can have the what? MSB over MSE. But in this case, we are interested in that of the treatment. Okay, we are not interested in testing if the blocking is significant or not. So our interest should be on the treatment. Okay, but the blocking is very useful. Okay, in form of the nuisance factor, but the effect is not of our interest. So with this, under the null hypothesis, under your H0, we have our F, degree of freedom of the treatment, which is A minus 1, comma the degree of freedom of the error, which is A minus 1, B minus 1. So we get your null hypothesis if the F observed is greater than F alpha A minus 1, A minus 1, B minus 1. In a nutshell, let me just quickly take you through this ANOVA table. We have the source of variation, we have the degree of freedom, we have the sum of square, we have the mean square, and lastly we have F. So under the source of variation, we have the treatment, we have the block, we have the error, and also we have the total. So the treatment, for the degree of freedom of the treatment, we use A minus 1. For the block, we use B minus 1. For the total, we use N minus 1. Don't forget that N is the same thing as A times B. So this is like saying AB minus 1. And for the error, we're going to use A minus 1, B minus 1. And this can be gotten using the same approach for the sum of square error we used above here. So for our SS, we prove this. We prove this, what our SS treatment is. The same thing with SS block and also SSE. So after you've calculated all this using the above value for computation, then you can do your MS, which is your SS treatment over A minus 1. Here you can have SS block over B minus 1. Here you can have SSE over A minus 1, B minus 1. And lastly, for our F, then we can have MS treatment over MSE. So you can make conclusion with your F, or you make use of what? Of the p-value. So this is where I'm going to stop for today. Thank you very much for watching. See you next time.